effectively. So when you have a user A and B packets, they can share a given network resource, and each packet uses a full link bandwidth. So if you have a 2 meg allocated to your link, then it will use up all of it as long as it has no contentions on it, because it's a shared network. So we are all sharing those mediums. Okay. Now, resource contentions usually happens when you have minimum bandwidth. So aggregation of resources can really exceed the amount of available bandwidth for a given link or for a given transmission. Scenarios what I was giving with the previous application on the circuit switching. If assuming that I've been given, assuming that you have to watch a YouTube video, that's about maybe 50 meg in size, and you only have 2 meg on your transmission, then chances are you're going to need what? Anybody, what do you know? What do you need? 2 divided by 50, what do you have? 25 seconds. Assuming you are measuring each and every 2 megabits within that 50 megabits of data, then you'd, in seconds wise, then you'd have 25 seconds to download all that 50 meg resource video from YouTube. So in that case, you're going to have some sluggishness. So if you want to really get that information at the speed of light, then within 1 second, then you also need what? A 50 meg bandwidth, because the data you access and it's for the video you access from YouTube is 50 meg in size. So if you want to get it quick in 1 second, you also need what? A bandwidth of what? A minimal bandwidth of what? 50 meg as well. So anything shy of that will always delay your transmission. Hence the reason why we say bandwidth, it's quite important when it comes to what? Packet switching. Because it's what makes a difference in any given transmission and the packet switching. If you have small bandwidth and you're accessing bigger volumes of data or bigger streaming information, I guarantee you're not going to enjoy packet switching. And I'm glad some of the ISPs have also understood some of these concepts. So what are they doing now? They're allocating a huge chunk of bandwidth to their subscribers. Or in our case, we have bundles. They say you can buy 5 gig or 10 gig for, say, 25 CDs, you know, for maybe a week or for a month. It all depends on the package, the package design, or its marketing or distribution business wise, you know. I'm trying to figure out the correct word to usually. It all boils down to how the package is being marketed. Okay, like for instance, I have fiber optic broadband at home. It's marketed at I'm getting 250 gig for 350 Ghana cedis a month. So that's a huge bundle, but it's not so much huge as compared to if I was getting a dedicated bandwidth. Okay, like what you have in developed countries, or what you call postpaid services. See, in this case, I have been allocated a bundle. So if I decide to use all of that 250 gig in one day, I would have to go back to the ISP and pay another 350 to buy another 250 gig. That's a shitty deal, if you ask me. The deal I want is, tell me I'm going to cap your upload and download to maybe about 20 or 50 meg bandwidth. And then you can use it to access unlimited data for the price of 350 CDs a month. That's a better deal. So I know I have unlimited, you know, access to information. But here's a scenario, because of the fact that we are idiots, we don't understand how internet are packaged in terms of packet switching. We try to rip the people off by giving them bundles. We pack a bundle for them and say, here, pay this amount, it belongs to you. As to whether you can use it out for the period, for a duration of time that you've been allocated to, it's up to you. If you want to consume all of that in one day, hey, more money for us. You come back and you pay more money for the bundle all over again. So it's a terrible deal. And these are some of the things that I feel like developing countries, guys, have not really accumulated or kind of like understood very well. mostly because of lack of education. Okay, lack of education has led to some of these issues. So the ISPs are basically taking advantage of our ignorance because they know we don't understand some of these concepts within packet switchings or data transmissions. Oh, those guys, they wouldn't understand that. So let's just give them bundles. Forgetting that, look, there are a number of they're unlimited resource on the internet today. So why are you giving me a cap bundle when there are unlimited information? So in a way, they're limiting what we can access on a day-to-day basis or on a monthly basis and charging us huge money. It's a good business for them, but it's a shitty deal for us. But this is Ghana. In the developed countries, nobody will fall for a bundle. No idiot will fall for a bundle because they know it doesn't make sense. It doesn't make sense. The internet is what? Full of gazillion resources. So why limit it to people? Instead, cap the app and download and upload. And tell us a month, you're going to pay this amount of money. For unlimited, resources, so you can access the resource unlimited anytime you want. But in Africa, in developing countries, the guys are idiots. They've not been educated properly. So they're comfortable with it. I'm pretty sure some of you are using your connections for this video. By the time it's done, or this Zoom session, by the time you're done, all your bundle has been exhausted. You have to go back again and pay for that bundle. That's a rip-off. They're ripping you off big time. All because of the fact that the ISP thinks you're an idiot. You don't understand packet switching or data communication networks. So I'm teaching some of these things, hopefully that when you guys get in some of those positions, you can make change because you have understood some of these things from courses like what I'm teaching you today. Are we good, guys? Math everywhere. Yeah, math everywhere, Masa. There's math everywhere. Obonu FM. Okay, yes. Yeah, so those are some of the things that we need to, address. Okay, so like I said, I'm hoping you guys will make some of these changes to let people know that, hey, we've gone to school. We understand some of these things. So we're not going to take that, ripping of people off like that. It just doesn't work anymore. Okay. Where was I? Okay, so moving on. For voice and data transmission, packet switching is divided into virtual circuits and datagram packet switching. Now, since voice asynchronous transmission, they require what you call a bit of the circuit switching because you cannot store and forward voice transmission. They are streaming live, they are live transmission, and they can be stored and forward and routed to different packets or different routes. So in that sense, for packet switching to address voice, and today, practically every communication is within packet switching. We've kind of like ignored or dumped circuit switching as more of an archaic technology or an obsolete technology. Every transmission today, it's purely under packet switching. But to get to, packet, you have to understand how circuit switching plays a role. But even within packet switching, you notice that to address voice transmission, they have to fall back on what? On circuit switching all over again. But in this case, they made a virtual version of it. So that way we can accommodate for the dedicated path to have a voice stream without any issues or without it being broken into packets and then routed through different networks or different paths, because you can't do that. Assuming that I said hi and the H goes through route 1 and then the I goes through route 2. By the time you receive it, you get the first maybe message you might get is and then later. It wouldn't make sense. It wouldn't make the conversation flow. Here's the reason why when it comes to voice transmission, we cannot afford to make it packet. We have to find a circuit relating transmission technology for it or implementation for it. So for packet switches to address voice within packet switching, they have to call on what? Circuit switching all over again. But in this case, they use the virtual form method by using various logical virtual gates through implementation algorithms to make sure that we can accommodate for voice transmission. But when it comes to pure data, it's another datagram transmission or datagram packet switching, where we can do the store and forward or non-live transmissions to be able to go through different paths or different routes before they get to what their final destination, because of the fact that data is not so much time dependent as compared to voice. Voice is time bound. Data is not time bound. Now, virtual circuit packet switching are used to address voice and other analog or continuous signals that require dedicated or prioritized path of transmission. So I just talked about that. Whereas datagram packet switching are used to address digital discrete signals that do not require dedicated path and can address or can accommodate for the store and forward like the internet data transmission is. So in terms of bandwidth, packets of non-fixed patterns like 10 meg on a 1.5 megabits link from multiple sources are accommodated within a shared link using what you call statistical multiplexing. So they have a different approach to modulating or multiplexing their transmission. Okay, and that makes it a bit more easier for us to share medium. So even if you have a link of 10 megabits on a given link that you are on, and your ISP allocates you maybe only 1.5 meg, you can still use it to address your transmission because 1.5 is smaller than what's 10 meg. So they're hoping that with that, you can be able to access your communication needs because of the fact that it's a packet switching. Most of the information you're accessing are not time-based, time-bound. They're all stored and forwarded, or they're all stored somewhere and you are accessing it in a non-live transmission. So 1.5 meg can accommodate that particular transmission. Okay, so if you're streaming a YouTube video and a video is about, going back to the same scenario again, it's about 50 meg and you have maybe 1.5 mega, then it just means that your transmission will be much slower, but at the same time, you're going to be able to stream that video without much buffering, as long as the minimum requirement to have that 50 meg come true to you is less than your 1.5 meg bandwidth you have at your disposal for your transmission. You should be able to address that. Okay. Ajit always has questions, huh? I like that, but we got to go through this. Okay, let me see if I can address your questions real quick. And then, Ajit, where are you? Yeah, what's up?
Yeah, sir. Good morning once again. Yes, concerning the YouTube video you are talking about, or you know, we have definition, we have high definition, and then we have
low resolution ones. Yes.
Yes. So talking about the 1080p, I think that one will fetch more data.
Exactly. Usually
you need more
the higher the resolution of a video content, of a media content, so when it comes to videos, the higher the bandwidth requirement. So if you want to watch high definition videos on YouTube, you're going to need a lot more bandwidth or a lot more bundle, as you guys call it today, or in Ghana or in developing countries, we have bundles. So we need a higher bundle to accommodate more of the high resolution or high definition video content. So you notice that when you're watching high definition videos, your bandwidth runs out faster or your bundle runs out faster. Yeah, that's because they require a lot more bundle to accommodate for that high resolution transmission. Okay. Yeah, some of the issues that we have to, that's what I mean by the fact that we don't need bundles. We need a cap of the upload and download, and then charge us an amount for a month. That's what we need, so we can have access to unlimited transmission. That's what I mean by the fact that in developed countries, the US, the Europe, the Asian countries, they've understood this. So there's no way in an advanced country where they have a bundle service. No ISP. Even the citizens will fight against it. Because they know for a fact that if you tell me you give me a bundle, you are cheating me. You're basically limiting the amount of information I can access. So just give me a capped uplink and downloads. And say, okay, I'm charging you this amount every month. That's all. So I can have access to whatever I want to access. If I want to access high definition videos, it's up to me. It shouldn't be your problem. Just make the infrastructure available for me, or the implementation available for me. Like I said, we Africans or developing countries have not understood that. So the ISPs are taking advantage of our ignorance. Hence the reason I'm saying I'm teaching you some of these things. So hopefully when you guys get into some of those positions, you can make the changes. Otherwise, your kids will come and they'll also be suffering. They'll also be ripped off, like the way you're being ripped off today. You're supposed to change your future generations' way of life. Are we good? I don't want a situation where I teach all the stuff, and then when you find yourself in those positions, like maybe you're CEO of MTN someday, and you're still insisting on bundles. Master, if I come and see, I'll slap you back. Seriously. It means you didn't learn jack for what I taught you in class. You're making life so continuously stressful and ripping us off. And that's not right. So make changes once you get in some of those positions. Or if your parents are there, teach them some of these things and tell them, look, man, it needs to change because we are actually suffering. We, the users, are suffering. We're the one paying the money. And then the coffers of these ISPs are bloated. Their CEOs take so much, thousands of dollars money in their salaries at your expense. Why? I mean, how much at all can you spend in life? Make resources available to users so they can make differences. They can change and transform the world that we live in or the community they live in with access to what? Unlimited information, but not capped information or bundle information. Good. Well, now let's move on. So this is how packet switching is handled within various network implementations. So we got a 10 meg transmission coming through from a device, but it has a link of only 1.5 meg. So the link that's carrying the information is actually smaller than what the request coming. So it's like you uploading maybe a YouTube video. So a video from your phone or from your video recorders onto a YouTube channel, and you actually carry your content is carrying 10 megabits, but the link that you've been assigned to by your ISP is only 1.5. So you notice it's going to be slower. So the math here is that if you're going to take, so you have 10 divided by 1.5. What is that? Anybody? What is 10 divided by 1.5? Let me just do the calculation real quick so we can see. So 10 divided by 1.5. That is 6.6 seconds just to upload that 10 meg into your social media content or your YouTube videos or your Facebook videos. It's 6.6 seconds. That's a lot of time. But assuming that the link that your ISP, Vodafone or MTN or whoever your ISP gave you was also 10 mega, then it means only 1 second is what you need to basically send that 10 meg video across the Facebook server to your channels or your YouTube channels or your Facebook profile. It's much quicker. So everybody's happy, you know. 1 second, yes. But when the link is too small, then everybody just starts, struggling. And keep in mind, it's not just you. You're probably sharing that 10 meg with somebody else. So in this case, you have two devices, A and B, sharing a 10 meg Ethernet transmission. And then the actual link that they have at the disposal from the ISP is only 1.5 meg. They're all going to struggle sending all kinds of information across. And that's where we use what you call the statistical multiplexing to handle all this information coming from the users. Even though it might be sluggish, at the end of the day, you're still going to get, it's just that time will take much longer. to get your information uploaded or sent across to a device that you're sending it to. Okay, so packet switching versus circuit switching. It's great for busy data, resource sharing is applicable, and it's simpler. There are no cost setups like we have in circuit switching. And then excessive congestion is also one of the deep challenges with packet switching because of the fact that there's a contention on, like for instance, we have over here, you have only 1.5 meg and you actually transmit 10 meg. And then you even share that 10 meg with a different user too. So you have the contentions or excessive congestion coming up. So there are packet delays. Okay. So with the 10 meg going to a 1.5, you're going to take 6.6 seconds just to deliver the information. And sometimes you might have losses of packets on the route, more or less because of the fact that it's too congested. So protocols are needed for reliable data transfer to avoid congestions. And so we also do have congestion mechanisms or controls that makes excessive delays or packet losses or packet delays manageable within packet switching. Now, obviously, since packet switching has become the more or less the basis for most of our transmission, engineers have to go back to the drawing board and then figure a way to address all of these issues with congestions within packet switching or packet delays, packet losses, bufferings, high latency in general. They have to address that, and they address that using protocols, all kinds of design mechanisms, algorithms, and what have you, to make sure that packet switching becomes, or still maintain its reliability in terms of data transmission in a digital world. Question: how do you provide a circuit-like behavior where bandwidth guarantees are needed? There's a question over here. How would you provide? I think I've already answered this question in the previous slides. So I want someone to answer it for me. How do you provide for circuit-like behaviors where bandwidth guarantees are needed for, say, audios and video apps? Anybody? Any hands up? I answered this question already in the previous slide. So let me answer it again so you guys take note of that. Now, these are, according to this slide over here, or according to the question, they're asking for circuit-like behavior or transmissions that are circuit-like, like voice and audio. So voice, audio, voice, or video content. Or in this case, your video apps or your audio apps, like WhatsApp voice or Facebook voice. How does circuit switching accommodate that? It uses what you call the virtual circuit. So the virtual circuit is what is used to accommodate those, because these are information that requires dedicated path or live streaming or live transmission. They don't need to be packeted and then run through different routes. They have to be continuous. So with this, to address this issue, we need what you call the virtual circuit packet switching approach. So that's what you have on your phones these days. You have VoIP services or voice over IP, which is VoIP. The voice over IP are taking advantage, even though they are purely packet switching transmissions, they are taking advantage of the virtual circuit component of it to allow you to basically have voice calls or video calls on them and make it seamless. Very good. So that's how you answer that question, using the virtual circuit packet switching. Moving on. So advantages again continues. We have statistical multiplexing that are used for handling links with minimal bandwidth as compared to the actual bandwidth request that comes through, and that makes it much more efficient in bandwidth usage, and they're quite simple to implement. So packet switching is a lot more simpler as compared to circuit switching in its implementation. At disadvantages, we've talked about some of them already: excessive congestion. A lot of protocols needs to be put in place to make sure that there's reliable data transfer. Okay. And the hurdles, if you're going to have a lot of protocols, it really makes your headers quite high. So your header overheads are pretty high. Okay. All because of the fact that you need a number of protocols with their header information to add to your packets that comes through. And that makes packets headers quite bloated. But like I said, the whole point is to make sure that information is reliable. So we need those losses and delays within packet switching. So how do losses and delays actually occur on packet switching? So we want to look at how some of these delays and loss of packets affect packet switching, or how they even occur in the first place. So generally, packets are queued in a router's buffer or in router's buffers. When packets arrive, or the arrival rate to a link exceeds, when packets arrive with a rate that exceeds the output link capacity, then the packet must be queued. It's kind of like how you have 10 meg and then 1.5 meg link. You have 10 meg on at your end for a transmission, but on the actual link that you're supposed to send a transmission through is only 1.5. So in that situation, a router needs to basically queue the packets that come through, because of the fact that the link that's supposed to support your packets, it's quite not up to the capacity. So we'd have to queue it and then let them out as and when in the link is free to accommodate single packets. And usually when that happens, you would have a lot of delays or latencies, if not losses of packets. So generally, packets arrival rates to a link exceeds the output link capacity, then you'd have to have the routers or devices queue those packets and wait until the attempt comes up. And like I said, creates a lot of delays on a given transmission. So yeah, this packet being transmitted with a delay one by one, so until the 10 expires or until the attempt comes out before they get let through. There's the packet being queuing in delay as well, so it's free available buffers. So our packets can take up some of those spaces. Every router or network device buffer has also a limits to which it can absorb, which could be based off memory capacity or storage capacity on those devices. Usually when the buffers are all filled up and information comes through, we'd have to drop some of them until they're free. So we say usually if the buffer is filled up, then the packet needs to be dropped. So you have lost packets. Packets will only be made available if the buffer within the router has some free spots to accommodate incoming packets. Now there are four sorts of packet delays, and the first one is the nodal processing. Usually the delay comes from the fact that you have the overheads. So we need to check for bit errors, determine output links to make sure they can accommodate a particular packet's capacity. Okay. The other one is the queuing. Now, time waiting at output link for a transmission also creates that delay. It depends on congestion levels of the router as well. But generally, if you queue something if you're in a queue, you're bound to have some delays. So here is a diagram of how some of these things are looked at. Transmission is the packets going out into the main link. And then the queuing are the devices that are actually in the buffer. So the time between the packet coming through to a router's buffer to the time it actually gets exited out of the router into a given link is what you term the nodal processing. So it's going through more or less the routers, you know, system processing. It has to obviously go through the OSI model from layer 1 to layer 3, and then to understand which further information it's carrying in terms of IP addresses, destination address, and what have you. Check some of those bit errors. And other control measures needs to be looked at. So that process, that time process, which you tend to know the nodal processing. Okay. The third one is transmission delay, which is usually based on the link's bandwidth. So if you have a minimum bandwidth for a given link, then chances are you're gonna have delays. If the bandwidth is much smaller on a given link than the actual data that needs to go through, it's going to be a delay without any doubt. Okay, so a bits per second going through that bandwidth is delayed. And then the packet length, if the packet length is bigger, so assuming you're transmitting larger packet length of bits, then you have to have some delays over there. Now, time to send bits usually into a given link is equal to the packet length divided by the bandwidth. Okay, so time to send bits into a link, it's usually calculated based on the packet length and the link bandwidth. Okay, the fourth one is the propagation delay. So here you have the length of the physical link itself. Okay. And then the propagation speed, which is measured in the speed of light. And then the propagation delay is calculated using, the length of the physical link divided by the actual propagation speed within a given medium. And it's usually 2 times 10 raised to the power 8. So that's a huge speed, meters per second. That's the speed of light, right? 2 raised to the power 10 raised to the power 8 is, or 2 times 10 raised to the power 8 is actually the speed of light, because that's how fast electricity moves, speed of light. Now note that S and R are very different quantities. So R is actually the link bandwidth, and S is the propagation speed. And propagation speeds are also based on how much electrical signals have been energized to go through the given link. That's what we say, that the link and then the propagation speeds are quite different. You could have a light, depending on the energy associated with it, might give you a lower speed. But the bandwidth is always the bandwidth, which is representative of the bits per second that it can take at a given time. Okay, so keep that in mind, that there are 2 different entities or quantities that you need to look out for. So nodal delay can be calculated, by saying processing speed plus queuing plus transmission plus probable propagation delay gives you nodal delays. Processing delay, which is d prod, typically a few microseconds or less. D is a queuing delay and depends on congestion. Transmission delays are usually obviously the L divided by R, which is the length and divided by the bandwidth, right? So the packet's length and then divided by the length. And then your propagation delay, so a few microseconds to calculate the, a few microseconds to hundreds of microseconds or milliseconds. So those are some of the calculation that I use to handle some of these delays that comes up on packet switching. Okay, there's also queuing delays, which is also based off the link delay, so the link bandwidth, and the packet length, as well as the average packet arrival rate. So when you're given some of these information, you can use it to more or less calculate traffic intensity. If you want to know how fast or how the response within a given link traffic, then you can use some of these information to determine whether you can have a delay or now what kind of delays you're having. And in this calculation, you just have to worry about your packet length multiplied by the average packet arrival rate, the time at which a given packet arrives. You use that, and then you divide all of that by the bandwidth of the link. And usually when the traffic intensity is equivalent approximately 0, we say we have an average queuing delay, which is small. When the traffic intensity is equal to or less or greater than 1, then the delay becomes much larger. So equal to or greater than 1, sorry, or equal to 1. And we say the delay becomes a bit larger. Now, when the delay, so when the traffic intensity is like bigger than 1, so this is more or less less than or equal to 1. When it's greater than 1, then there's more work arriving than can be serviced. At an average delay, it becomes quite infinite. Then an average delay becomes quite infinite. I think there's a typo here with the arrows. They're supposed to be, if I'm not mistaken, supposed to be greater than or equal, sorry, less than or equal to 1. If it's approximately 0, then it's average queuing. When it's exactly 1 or less, then you have a delay. So if it's maybe 0.1 blah, 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 then you have a delay that's becoming quite larger. The very moment it goes beyond 1, you do the calculation, the traffic intensity is greater than 1, then you got a lot more infinite delays coming up on your transmission. So this is how your queuing delays are observed for a given traffic intensity within a packet switch network. Packet losses, queue preceding link in buffer. When they have infinite capacity, then you might get a packet loss. So if the queues or the information coming through, the packets coming through are quite bigger than the capacity of a particular buffer size, then you're gonna have packet loss. When packets arrives to a full queue, packets also drop because the queue is already filled up. Lost packets may be retransmitted by previous nodes. That is, if they're able to get the acknowledgement that the packet that was sent did not get the right response that it needs, then they would have to retransmit, which most devices have been robustly designed or intelligently designed to know some of these things. There's a time given for response or for acknowledgement to be received. If they don't get that, then they know the packet either got dropped or lost in transmission. So they need to retransmit all over again. Okay, so retransmitted by previous node, either through source end system or not retransmit at all. It all depends on the system you're dealing with or the devices you're working with. Okay, so on that note, we'll look at the reading chapters for this particular topic, and it's on that Chapter 10 of William Stollen's textbook from Session 10.1 to 5. So that's where you'd get in-depth knowledge on switching technology. I hope you can read those chapters or those sessions so you can be a bit more, informed. As I said in class, this is a PowerPoint note or PowerPoints basically So it doesn't contain all the actual, I mean, I couldn't fit the entire topic or chapter within the PowerPoint slides. 26 slides, it's just not practical. So I would expect you to go back, or hence the reason why I have the reading chapters at the end of the slide, so you can go back and read them and get the, you know, the more meat or the more knowledge that you need about this particular topic. Or if you want to get a much better understanding, then you have to go back and read the topic or the chapter. Okay, folks, so that's pretty much answered for this particular topic. And I hope I covered some of your questions and your and I was able to answer some of your challenges. And I hope you also learned something. Okay, then. So let's call it a day, guys. And I'll see you on the next one, which is next week, right? Okay.